let's talk a little bit more about mechanisms and deriving the rates for multi-reaction mechanisms. So let's suppose we have some mechanism that we're proposing for A going to B going to C. So these are all single reactant elementary steps, and we have some unknown rate constants, K1, K2. So again, because these are elementary steps, we know that this step is a first order reaction. So dA dt equals negative K1 times the concentration of A. Similarly, B is going to have two first order reactions related to it. So B is getting formed from this. So dB dt equals K1 times the concentration of A. And then we're losing B in the second first order reaction step. So this will be minus K2 times the concentration of B. And then dC dt is just going to be equal to K2 times the concentration of B. So this reaction, again, A is our starting material. That's what we put into our reaction flask. And then we get out C as a product. So we don't really know what our concentrations of B maybe are over time. So, but we do know A at time 0, because that's what we put in. So we're going to solve this as usual. So from integration of this reaction, we know that A at times t is going to be equal to A at times 0, e to the minus K1 of t. And that's just the integration of a first order reaction. So we've done that already, easy peasy. So now that we have this expression, we can substitute this into this expression here. So I won't go through all the math. If you want to come talk to me in office hours. But by substituting this in, we can then express B at times t. So B at time t equals, let me make sure I get this right. It's going to be equal to K1 A at time 0 over K2 minus K1 e to the negative K1t minus e to the negative K2t. So as you can see, these exponential decays are because positive and negative are because we have two first order reactions involved here. And then this is just solved by the substitution. OK. And then finally, we take this expression, then here. So this expression substitutes in. Yellow is very similar to green, by the way. So this goes into here. And then we should be able to get out that C at times t equals, OK, hopefully I don't get cut off. This is going to be equal to A times 0 minus 0 over K2 minus K1 K2 e to the negative K1t minus K1 e to the negative K2t. So even though C looks like a very simple first order rate expression, because B is more complicated, then C is getting more complicated also. But what we have now is that we have expressions for A, B, and C all in terms of what we know, which is our initial concentration of A, as well as our two rate constants, which we don't know. But we could eventually apparently fit our data to these expressions. OK. So what do I mean when I say a rate determining step? What I mean is that if K2 is much, much bigger than K1, or K1 is much bigger than K2, these two steps happen at very different rates. So because of that, we have kind of extremes that we could then plug into our scenario that might simplify our expressions. So let's suppose we have our case that, so if K1 is a lot smaller than K2. So what this means is that this second step goes a lot faster than this step. So this is what we would call our slow step. slow, and then fast for this scenario. Okay, so let's look at our expression for c at times t. So I'll rewrite that up here just because it's a little hard to see. So we said that c at times t equals a times 0 minus a times 0 over k2 minus k1 times k2 e to the negative k1t minus k1 e to the negative k2t. Okay. So what we're saying is k2 is very, very big, k1 is very, very small. So what this means is that if we think about this number, this is going to be approximately equal to k2. And so then we start thinking about canceling things out. So then this k2 should cancel out. And also this should go to 0. Because, by which I mean because k1 over k2 is going to be approximately 0. So, okay, that's our simplification, which means that if k2 is very, very much larger than k1, c at times t is going to be equal to a at times 0 minus a at times 0. So remember, these k2s canceled out because they divided by each other, times e to the negative k1t. But look at this expression. This expression is the very same one that we would expect from here. So this looks like a first order reaction, rather of comparing if we had just, right? This looks very similar. So this is what we would have if we had A basically going K1 to C. This would be the same answer that we would expect. So what this means is that the slow step is the rate determining step, because this fast step is so fast that it doesn't affect our rate. That's why this was our rate determining step. Rate determining step. Okay, voila. If, on the other hand, we had a different slow step, so if we had this scenario where, let's say, this was slow and this was fast, so this is my second hypothetical scenario. If K1 is a lot faster than K2, we would then look at this expression. So again, let's see. So let me write this again. Bear with me. So this is again just the actual expression. Okay, so K1 is a lot bigger. So what this means is that this is approximately negative K1. This will go to 0 because this fraction, again, because K2 over K1 is approximately 0. And then, again, these negative K1s would cancel out. So that would divide by itself. And then, so then, therefore, C at times T equals A at times 0 minus A at times 0 e to the negative K2t. So again, you can see that this now, K2 is a rate determining step. So second step is rate determining. So, okay, so again, having a very, very slow step will kind of dominate our overall kinetics. That's kind of the real takeaway. It gets a little bit more complicated as our reaction mechanisms get a little bit more complicated, but this kind of illustrates what we mean by rate determining.